Hello, good morning everyone. So today we are in the second class of the structural dynamics lecture. Just to recap what we have studied in the last class. So we did primarily, we try to understand how we can able to make some mathematical model consisting of the single degree freedom system, multiple degree freedom system and the continuous systems, and also what type of output we are actually expecting once a structure is subjected to the dynamic load. And after that we have tried to make a simple mathematical model which is known as the single degree freedom system. So there we have seen how we can able to idealize the mass, how we can able to take the stiffness, and what could be the first type of solution once we are considering the system is undamped and it is vibrating freely, means we are not applying any external forces on that structure. So we have seen how we can able to solve the complete thing, how to formulate the differential equation for that, and how we are solving each and every unknown coefficient from the initial condition of those differential equation. Okay. So before we go to the next one, do you have any questions? We can then discuss that thing. Okay, so if there is no question, then we can go ahead further. And we have also seen that how those graphs look like in the MATLAB software. So now if you see, in the last class, once we have done, we have assumed that this is mass and this is stiffness. Okay, but we considered that our system does not have any sort of damping. So now our main equation of motion was, I'm just writing here, mx double dot plus kx, that is equal to 0, because we are not applying any forces on that. So now once we are going it today, so we will first write the same thing. So now our system, we are having the spring coefficient k, we are having the mass m, and additionally we are adding some sort of dissipation or damping c. Now if you see in practical case how the damping comes, so before we go how the damping comes, we try to understand how the physical phenomena is occurring. So if we see any structure is oscillating, we see that slowly the amplitude of the oscillation get reduced and the structure eventually comes to the rest if we are not applying forces continuously to the structure. Okay, so once we are doing that, in that case, and in the last time once we solve the single degree freedom system undamped, we have seen the oscillation never get decays, its amplitude remain constant throughout the thing. So that is not the practical representation of the system, because the system is losing its energy. We have seen also, like once we vibrating scale, we see that the scale comes to the rest. It is not endlessly vibrating. Why this thing is happening? Because like once we are vibrating the scale, it is also moving the air present in surrounding portion. So that air gives some sort of viscous damping on that structure. So therefore the vibration of the structure is reducing slowly. Okay, so that effect we have to also consider into our model. Then the model will become more realistic, and now we can expect to see that our vibration will no longer continues, rather it will start decaying slowly. Okay, so let's see. So therefore from that assumption we put one dissipation mechanism, so as a dashpot. Okay, so now if I try to again do the force calculation, so obviously like we are assuming that it is displaced by x amount, so the inertial force will be mx double dot, then stiffness force will be kx, that is the elastic restoring force, and damping force will be cx dot. And damping is mostly proportional with the velocity. So we can see mass is multiplying with the acceleration, so mass is contributing with the acceleration, stiffness is contributing with the displacement, and damping is contributing with the velocity of the full thing. Okay, so how we can able to write our equation? Mx double dot plus cx dot plus kx, and if we are having some force, that will be equal to some force. But for our case, like once we are doing for the free vibration, so for free vibration, the F should be equal to 0. So for free vibration, we can write mx double dot plus cx dot plus kx, that should be equal to 0. Okay. Previously, if you remember, we assumed that cx dot is not there. Now we are having cx dot into this. Okay. Very good. Up to this stage, do you have any question or any doubt? I think this is very straightforward thing. Perfect. So now, first thing, once we so this is a differential equation. What is the order of the differential equation? Second order. So again, if we just try to write it, it is a second order ordinary. Anything else? Homogeneous differential equation. Okay. So, and also constant coefficient, because m, x, c and k are not changing. M, c and k are not changing in that. So, they are the constant coefficient. So, what the solution we can assume? A into e to the power of lambda t. Okay. Some of the cases you may see that people are assuming the solution x equal to e to the power I omega t. That is also absolutely okay, because if you see in the last case, you can see that our solution came that lambda equal to plus minus I omega. So automatically you can see that if we are assuming x equal to e to the power of I omega t, that is also okay, not a problem. Okay, but if we are thinking from the original differential equation point of view, then it is always better to choose it e to the power lambda t, because you don't know what type of lambda will come. So why to presume that it will be a complex number or it will be imaginary number? There is no need actually. If it is a complex number, it will eventually comes to be a complex number. That's all right. As we see that previous case, it is automatically become a complex number. So we better use this one, this notation, that a into e to the power omega t. But don't get confused if you see in any book that it is taken e to the power I omega t, fine. Or if you see anywhere it is started with a cos omega t plus, means a cos omega t plus b sin omega t. That is also okay. We have seen in the last class that we can also able to take that solution as well. Okay. But I personally do not prefer to take cos sin, because what happened, if you see a 2 degree of freedom system, it is all right to have like a cos and sin. But suppose if you are solving a 4 degree equation, then maybe you will choose cos sin, cos hyperbolic, sin hyperbolic. After that, what will you choose? In several cases, we have encountered 6th order, 8th order, 12th order, different types of polynomials. So in that case, we will be losing our options. So it is always better to choose e to the power lambda t. Whatever the power of lambda is there, that many roots of lambda will come, and automatically you can write your solution accordingly. So there will be not a problem at all. So it is best to choose e to the power lambda t. So it will serve the global perspective. Whatever the order of lambda, hardly matter, not a problem. Okay, so suppose if we choose that, we will going to substitute it. So I think in the last class we have done. Again, I can just write it once more time. This is that, and then if we are doing the double dot, it will be lambda square a e to the power of lambda t. So suppose if I am just substituting m lambda square plus lambda, sorry, m lambda square a e to the power of lambda t plus lambda c a e to the power of lambda t plus k a e to the power of lambda t, that should be equal to 0. Okay. So m lambda square plus lambda c plus k into a into e to the power of lambda t should be equal to 0. Okay, so now my characteristics equation become this: m lambda square plus c lambda plus k, that is equal to 0. Okay, so characteristics equation k equation will be m lambda square plus c lambda plus k, that is equal to 0, because other two cannot be 0. A is the amplitude, that cannot be 0. E to the power lambda t is also the solution, that cannot be 0 as well. So obviously if they become 0, then the solution will become trivial solution. So for the non-trivial solution, this should be equal to 0. So now if this is the equal to 0, then what should be the value of lambda? How can we able to calculate? Lambda equal to minus b plus minus root over of b square minus 4ac by 2a. Okay, that is a very well known formula to all of us. So if I see, then minus, b by 2m plus minus root over of c square by 4m by k divided by 2m. Okay, that we can say is our lambda, and we can have the two solution. One is lambda 1 and another is lambda 2. So lambda 1 will have first one is the plus and then second one is the minus sign. Okay, I think that is very clear. Now here this has, once this thing comes, now you can see that this determinant has a, this portion has a big role. Why? Because these will judge whether the solution will be a imaginary or whether it will be real. Okay, one thing is for sure, that c, m and k all are positive real number, but they cannot be negative. Your mass cannot be negative, your stiffness cannot be negative, and your damping also cannot be negative. Okay, so c, m and k, so I can just say that c, m, k all are greater than equal to 0. No problem on that. Definitely they should be positive. So this portion, if I just say this is the delta, and maybe I am just writing again that lambda equal to minus c by 2m plus minus root over of delta by 2m. So that delta, which is equal to c square minus 4mk, that has a big role. So now if delta is greater than 0, that means c square minus 4mk is greater than 0. So c square is greater than 4mk, then that means c is greater than 2 root over of mk. Okay, do all of you agree with me? Makes sense? Should I need to put plus minus here? No question, because c, m and k all are positive. So suppose if they all are positive, then c minus here cannot be possible, because c is not a negative number. So you don't need to write that minus thing. Okay, so you will have this. Now if you remember, we also mentioned last time that the natural frequency of the system, that was omega n. So omega n was equal to root over of k by m, and here we have, so suppose if I just say that k equal to how much it is, m omega n square. Okay, you should pay one little attention, because here we are using omega n. Omega suffix n is denoting the natural frequency of the system. Okay, that means like if we are leaving the system, how it will naturally going to oscillate. It is a system's property. Okay, because you can see that it depends on the mass and stiffness. It is not depending on anything the way you are exciting it. It doesn't bother at all. Okay, it has its own thing. Okay, so suppose if I just try to write that thing here, so C equal to 2 m into omega n square. So I can write C equal to m omega n. Okay, so if this is this, and now I am also introducing one term, that Cc, that is equal to 2m omega n. Okay, so then what can I say? This C is greater than Cc, and this C, let's define this as the critical damping. Okay, so this is the critical damping. You can see the importance of the critical damping is what? If your C is equal to Cc, that means this delta will become 0. Exactly. So if C is equal to Cc, that implies delta will be equal to 0. Okay. If C is greater than Cc, that implies delta greater than 0. If C is less than Cc, that implies delta should be less than 0. All of you agree with me? Agreed? Everybody? Any doubt? Any doubt? Okay. So we can say that this is one of the very important point where C is equal to Cc, because it actually giving the bifurcation of the two solutions. Once C is more than Cc, it is having some type of more higher level of damping, and then it is having some lower level of damping, and more importantly we can see the solution get changed. The characteristics of the solution get changed, that one is become complex enough solution, and in another case the solution remain a real solution. Okay, so now let's see, and if you could try to remember in the last case what was happening, solution was real or imaginary? Imaginary. Very good, perfect, solution was imaginary. So now if I just try to write it down the complete thing, so just try to remember that lambda equal to this form. So I'm just taking this one, that lambda equal to minus, I can just write it, lambda equal to minus C plus minus root delta divided by 2m. That is my lambda, and delta is C square minus 4 km. Okay, or I can say C square minus Cc square, and Cc equal to 2 m omega n. Okay, these are the 4 things we got. Okay, now important point is where, so now let's see first thing, that if C is less than Cc, if C is less than Cc, oh no, sorry, first case you take like C is equal to Cc. Okay, C is equal to Cc, so what will be the lambda? So C is equal to Cc means delta is equal to 0. So my lambda have solution this, and please remember we cannot have a single solution of lambda, so we can say that both of the roots are having the same solution. Lambda 1 and lambda 2 both have the same solution. So if this is the case, what will be my x? So here lambda 1 and lambda 2 both will be this much, because other portion becomes 0. If this is the scenario, then we can say x will be equal to a1 plus a2t into e to the power of lambda t. Sorry, e to the power of lambda t. Maybe I can just assume this is equal to lambda, or it can be also written like this way, a1 plus a2t into e to the power of minus c by 2m into t. Please. Yeah, that is actually the form of the differential equation. Like suppose if you are having two coefficient constant, same coefficient came, you like lambda 1 and lambda 2 both become same coefficient, you cannot able to write like in the previous manner a1 into e to the power of lambda 1 t plus a2 into e to the power of lambda 2 t. That doesn't hold because lambda 1 and lambda 2 are same. So both of these functions become same. You cannot able to distinguish those things. So you need to change the interpolation function. So what is that function? That function we are writing like a1 into e to the power of this plus a2 into t into e to the power of lambda t, because lambda 1 and lambda 2 are same. Perfect. Thank you for asking this. Okay, so we have this one. Any doubt up to this stage? Very good. So that is one of the solution we get. Now if we say that C is greater than Cc, that means lambda is greater than 0. Agreed? So lambda 1 and lambda 2 will be minus C plus root delta by 2m and minus C minus root delta divided by 2m. These are the two solutions we can get. Okay. So here the solution will be x equal to a1 e to the power of lambda 1 t plus a2 into e to the power of lambda 2 t, as like the previous case, because here lambda 1 and lambda 2 are the two different numbers. So we don't need to be worried with that. Got the point, na? This just only you have to pay attention once lambda 1 and lambda 2 are equal. If lambda 1 and lambda 2 are not equal, no, life is simple. No issue. You just straight expand that way. No problem at all. So here maybe I would like to take few minutes on that. Suppose if you are solving like a 12th order equation, you will have 12 number of lambdas. There maybe you may found that 4 lambdas are same and remaining 8 are different. So in that case you should write like this way, that a into 1 lambda you use plus second one with t into e to the power of lambda like 1 maybe I'm just saying. So first one maybe 1 1, then 1 2 will be t into e to the power of lambda 1 2, then t square into e to the power of lambda 1 3 t plus t cube into e to the power of lambda 1 4 t, and then again it will be e to the power of lambda 5t, lambda 6t, lambda 7t, because they are different, they can be easily put. But for the first one you have to do like this one, because there the lambdas are same. So as many as lambda will be same, you have to multiply that variable with it, and then you have to do that. So we have this thing x equal to this one, done. Then x we are getting this now. Yeah. So now suppose if I try to substitute this one here, so what can I see? A1 lambda 1 e to the power of minus c by 2m plus root 2m into t. Is that better? Okay. A2 e to the power of minus c by 2m minus root m by 2m into t. Okay, I get that. Now I think you can remember, suppose if you have a to the power, like let's say x to the power a plus b, we can write x to the power a into x to the power of b. Very simple, just to recall that thing. So I can write can I write it? Okay. Which one is common from here? That is common. So you can take that thing out. So we left with Okay. Now, if we try to see little bit more, we are having C by 2m. Okay. The first term is that C by 2m. So if I see, can I write it? C by Cc into Cc by 2m. Okay, I can do that. So C by Cc is what? A ratio of the damping present with the ratio of the critical damping. So this is known as the damping ratio, exactly, xi. Okay. And what is this term? Cc by 2m. I can see here Cc equal to 2m into omega n. So this will become just only omega n. Cc by 2m will become omega n, because already this is that. So if I just do Cc divided by 2m, that will be nothing but omega n. Simple. So my first term is becoming like this. So I can write e to the power of minus xi into omega n into t a1. Now let's see what is that delta. Okay, up to this stage, no problem. Any problem up to this stage? Anybody, if you have any question, any doubt, please feel free. Okay, no issue. Okay. So then delta will be equal to c square minus 4 km. So what can I write? C square. So here, yeah. So I can equal to k. I can so first case I can put k equal to m omega n square into m, and c I can put it. So I can see that here I assume c by cc equal to xi. So can I say c equal to xi into cc and xi into 2m omega n? So cc equal to 2m omega n. Can I write that? Very good. So here can I write it? So c square equal to 4 into xi square m square omega n square. So you can see 4 xi square m square omega n square minus 4 m square omega n square. Can I say that? Okay. So delta can be written like 4 m square omega n square into xi square minus 1. So we have root of xi, root of delta. So that will be 2m omega n into root of xi square minus 1. All of you agreed with me? Agreed? Very good. So that thing is also very important point at that stage, because if we see, we are having a delta which is equal to 2m omega n root over of xi square minus 1. Now, what is the value of xi? Once c is greater than cc, then xi is more than 1. Definitely, because xi is defined as c by cc. So if c is greater than cc, that means xi is greater than 1. So xi square minus 1 will be greater than 0. Greater than 0. So it will be a positive number. Exactly. And once it is a positive number, means xi square minus 1 becomes a positive number. So its root will be a real number. Okay. And if the xi is less than 1, that means c by cc is less than 1, then this thing will become an imaginary number. Okay. Makes sense? Anybody has any doubt? Okay. So let's try to write it. So e to the power of, and here once we are substituting it, we can see that we are having root delta divided by 2m. So in this case, we can say this is omega n into root over of xi square minus 1 only. Okay, makes sense. So once I am substituting this one here, so I will have only omega n into root over of xi square minus 1 into t plus a2 into e to the power of minus omega n into xi square minus 1 into t. That is my solution. Anybody has any doubt or any question? Anybody has any doubt? Okay, if you do not have any doubt, okay, then I will just copy that portion to the next one. E to the power of okay, that what we got. That will be my estimate. Okay. So now let's say that omega into root over of xi square minus 1. Yeah, so now we see that, so this is the some type of solution we can have. So this is for, yeah, so now there could be two cases. So one case, so one condition is that like C is greater than Cc, that means xi is greater than 1, okay, and delta is greater than 0. That is one case. So this case is known as overdamped system. Known as overdamped. Okay. First case, once we are having xi equal to 1, that was the critically damped. Now this is overdamped. Okay. Now another case is C less than Cc, that is xi is less than 1, that is delta is less than 0. Now one point I would like to you to pay attention on that. Once this thing is a real number, like let's say we are having something e to the power of, let's say some number, maybe x, or maybe just I can put it like this, maybe should I say, yeah, maybe like 2t, e to the power of 2t, or if we are having e to the power of minus 2t. How the graph should look like? Yeah, so e to the power of minus 2t is like a exponentially decaying graph. Exactly. And e to the power of 2t is exponentially increasing graph. So you can see that when we are writing this type of thing, we are actually taking these two as the two potential solution and we are scaling them up, because that a1 and a2 are nothing but the scaling. We are scaling that function and then add these two to get a function properly, to describing how it is actually working. Okay, but the point is where if we are having some complex number here, like let's say e to the power of I or maybe I to t, how should it look like? Because one case which is like a positive number, like for example this is a real number, if this is greater than 1, fine, it will be having like this type of solutions, perfect. Now if it is a complex number, because other case it's a complex number, how it should look like? Exactly, because in the last class we have done that. It is nothing but the Euler series expansion. We should do that. Cos 2t plus I sin 2t. Simple. Make sense? And it will become oscillatory, or maybe the sinusoidal, you can say. Okay. And there we are taking like this way, that the two mutually orthogonal, and then we are taking that with the summation form. Very good. So now tell me, if you are having completely real solutions of lambda, like for example this case, if I think that xi square minus 1 is greater than 0, so you are having first term is a, so first let's see the first term, because that term will not going to change by anything, whether you have delta greater than 0 or delta less than 0, doesn't matter, this term will remain same, xi into omega t, and we have a minus sign there. Now if you see, xi is nothing but c by c, that's a positive number. It could be less than 1, it could be greater than 1, it could be 1, but it is a positive number. So xi is a positive number, so xi is always greater than 0. Okay, omega is root over of k by n. K is positive, m is positive, so root over of k by m, that will be also positive. No question, it's a natural frequency of the system, it cannot be also a negative number, so it is also a positive number. So now minus xi omega t, that will be a, how it look like? It's a decaying graph. So this thing is like a decaying graph. All of you agree with me? Agreed? Agreed? Agreed, yes or no?
Yes, sir.
Yes, very good. So we see that this term, whatever is that, it's a decaying part. So we have left with this part. And additionally, another very important point, this part has no condition from the initial, means this has no dependence on the initial condition. There is no a1, a2, nothing. It is just e to the power of minus xi omega t. That's all. It is decay, always. Now you have left with the portion which can be decaying or which can be oscillatory, based on whether it is overdamped or underdamped. Make sense? Clear? No doubt? Very good. So if we can see that this portion is a real number, then we will have a decaying solution. So the solution will decay, and it is multiplied with a decaying function. Okay, so it will decay only. Decay, it is itself decaying, as well as it is multiplied with some decay function, so it will decay automatically. But in the other case, once xi is less than 1, so this is the overdamped case. Now for the underdamped case, if I see, then x will be equal to e to the power of minus xi omega t, that is constant, a1 into e to the power of I, okay, I omega into root over of xi square minus 1 t, and in this case I may be able to write it 1 minus xi square, because I already know that xi square is less than 1, and that's why I take the I out. Okay, clear? Why I am writing 1 minus xi square? Because I already know that xi is less than 1, so I unnecessarily do not make the root complex, and that's why I take I out from that. Plus a2 into e to the power of minus I 1 minus xi square into t. Okay. Now if I assume that omega into 1 minus xi square, that is equal to omega d, damped natural frequency. So what can I able to write? E to the power of minus xi omega t into a1 e to the power of I omega dt plus a2 e to the power of minus I omega dt. Okay, can I do that? I just substituted, come, it's not a big deal. Okay, now I would like you to please match this equation with previously derived. Equation like this. Look, they are very same. they are exactly same, just instead of omega we are having omega t there. Other all those things are same, but we have a multiplied term to the power of minus xi omega t, that's all. So instead of omega we are having omega t. Okay, so just maybe I will just try to write both the things so that we can easily compare that two things. So that is like undamped, maybe I just put x ut, that is x undamped, that was a1 e to the power of I omega t plus a2 e to the power of I omega minus I omega t. That was the solution. Okay, what we have derived in the last class. Now if we are comparing these two things, we can see that this portion and this part are almost same, except the change is instead of omega we are having omega t, and additionally this portion is multiplied into the power of minus xi omega t. So how this thing looks like, this thing should look like. We can also able to do that using MATLAB and try to see, but first try to imagine how it should look like. So we will have this portion is like your continuous function. Now you are multiplying it with a decaying function. So this thing multiplied with something like that. So what it will happen? It will be decay like this, where this e to the power of minus xi omega t is act like a envelope of that, and all the peaks should touch this thing. Just assume this is touching, because I am drawing by hand, it's not possible to draw like that way. Okay, so we can easily able to see that it's like an envelope of that full oscillation. Does that make sense? Hello? Does that make sense? Good. Any question up to this stage? Do you want to visualize the problem? So we can see very clearly that in this case we will have this type of oscillation, but in the other two cases solution should not oscillate, because there is no oscillatory part. Because oscillatory part is only present once you are having this portion with a imaginary coefficient. Without that imaginary coefficient it cannot oscillate. Because in Euler's theory, if you just remove that I, this will no longer remain cos, because there I will come. Means if we just would try to do it like e to the power of t only, then it will become cos of it plus I of sine it, and this will nothing but cos of hyperbolic t plus I sine hyperbolic t. So instead of its cos and sine function, it will become cos hyperbolic function and sine hyperbolic function. And they do not look like oscillatory wave, sorry. They are like exponential functions. So, and we can also see that means a real number, we don't need to do the Euler transformation. Okay, because we do Euler transformation to get rid of the imaginary number. And in the real, if we are again doing the Euler transformation and we are bringing the imaginary number into ourselves, so that makes no sense. So we can easily see that it's exponential function. So they are not going to oscillate. So in the first two cases, so what can we conclude from here? So C equal to Cc. So that means xi equal to 1. So that gives me the solution x equal to a1 plus a2 t into e to the power of minus xi omega t. Am I right? That gives me this solution. So this solution should look like how it should look like. Think. We should not do only in MATLAB. We should also try to visualize the equations. Exactly. This is the decaying part. Very simple. A plus, and this is something like a straight line equation. So it's a straight line. Try to go, but it get decayed like this way. Now think, if we are taking t a very high value, where the solution should go? 0. All of you agree? Okay? Yeah, it's asymptotically 0. It will never be exactly 0, but it's asymptotically become 0. Okay? So it will be have solution like that. Okay? Now if we, so this is the critically damped case. We should see the solution goes like this. Now if we are having C is greater than Cc, in that case xi is greater than 1, then we are having solution A, no sorry, we'll have e to the power of minus xi omega t into A1 e to the power of I omega dt plus A2 e to the power of minus I omega dt. Okay, that we will have. Okay, so this solution should look like how it should go. So if it is greater than that, means we will have root over of xi square minus 1 into omega t, root over of xi square minus 1 into omega dt, omega t. So in that case, the solution should go somewhat like this. Okay, because all are decaying solutions. Once C is less than Cc, then xi is less than 1. That means x equal to e to the power of minus xi omega t into A1 e to the power of I omega dt plus A2 e to the power of minus I omega dt. That solution should this. Okay, all of you agree with me? So there are 2-3 things we can quickly check. One is omega, that will be root over of k by m. One is omega d, that will be 1 minus xi square into omega, and xi is c by cc, cc equal to 2m omega. Okay, any doubt up to this stage? We see more or less all the solutions how they should look like. Now again the question comes, how should we calculate the value of A1 and A2 as like the last case? How should we do that? Initial conditions, very simple. So maybe we can try for the first case how to calculate it. So let's assume for the very first case that C equal to Cc, we have C equal to Cc, we will try to calculate A1 and A2, and all the cases initial condition is x0 and x dot 0. So these are the simple assumption. So if my x is equal to A1 plus A2t into e to the power of minus xi omega t, what will be my x dot? How to calculate? So we should understand that this is something like u and v, because both the thing has term t. Do not think that first term is a constant. No, first term is also have t. Okay, so we should do like this way, du dt into v plus v into the plus u into dv dt. So first portion it will be a plus this one, so this one will become a2 into e to the power of minus xi omega t, and second part, if I just think, that will be a1 plus a2t into e to the power of minus xi omega t multiplied with minus xi omega. So if I just try to take all the terms, then I will have a2 minus a1 xi omega plus, not plus, minus a2 xi omega t into e to the power of minus xi omega t. That will be my x dot. So if I put x0, that will be nothing but how much? That will be 1. So a1 will be my x0 and x0 dot will be a2 minus a1 xi omega, and this one is 0. So this one will become 0. So this. So I can write a2 minus x0 xi omega. So a2 will be x0 dot plus x0 xi omega. That will be my a2. Okay. So my entire solution should look like this. That is x equal to a1 is x0 plus x0 dot plus x0 xi omega into t into e to the power of minus xi omega t. Okay. So next one we have x equal to a e to the power of minus xi. So okay, so what we got actually? Sorry, let's little bit thought about it. So we have x0 dot this into t. So can I calculate when x will become 0? At what time t x will become 0? Possible or not possible? So because e to the power sin omega t is there, so and also that is another one is a linear function, so it's a difficult thing actually to calculate on that sense. Okay, good. Now next one we are going a into e to the power of xi omega t. No, not a into this one. E to the power xi omega t into a1 e to the power of xi square minus 1 omega t plus a2 e to the power minus xi square minus 1 omega t. Okay, that's my x. That is a overdamped system. Okay, so if I again try to do the differentiation, how it should look like? X dot will be e to the power minus this with minus xi omega into the same thing plus e to the power of minus xi omega t into a root over of xi square minus 1 omega a1 xi square minus omega e to the power root over of xi square minus 1 omega t plus, not plus, minus root over of xi square minus 1 omega a2 e to the power of minus xi square minus 1 omega t. Okay, that I can get if I do the differentiation of it in the same manner u and v. Okay, we'll get that. Obviously we have to rearrange. Okay, and you can do that thing, rearrangement easily. I don't need to do that. So in all those cases, what you will get, you can see that there is primarily this man is always going out, and you will have some term with e to the power of minus the square 1 omega t plus some term e to the power of minus omega t. Definitely, because this full thing can go common from the full term, so that is always common. Other things will be multiplied, pre-multiplied, taking the common, and you will have majorly these two things with some coefficients here, some coefficients there. Maybe I'm just assuming C1 and C2. Okay, so there will be some sort of like a minus xi omega plus into A1, and then maybe with A2 some portion will come, like this way it will happen. Okay, and we can able to get that solution. So again we will substitute x equal to 0, t equal to 0. We can calculate what is the x0. Again we will substitute at x dot this thing, and we can able to calculate all those things. We can do in this way, not a problem, and we can able to get the solution. Okay, you can try that thing in home also, do that full calculation, and we can go to the next one as well. So in the next one you can see that will be e to the power of minus xi omega t into A1 into e to the power of I omega dt plus A2 into e to the power of minus I omega dt. In that case, the advised portion is that to change it to C1 cos omega dt plus C2 sin omega dt. You may be remembered in the last class we did that transformation. A1, A2, we go to the C1, C2. So first you do that. Then what can we do? We can calculate again what will be the x dot. So x dot will be e to the power of minus xi omega t into omega d will be going out. That will be C1 sin omega dt plus C2 cos omega dt minus xi omega t e to the power of this into C1 cos omega dt plus C2 sin omega dt. So if I just try to again reassemble the full thing, I will get what? Cos, so that will be omega d into C2 minus xi into omega into C1 into cos omega dt minus you can just take it out. Okay, you will get like this one. Okay, now what you can do, you can now put like x equal to 0, so you can able to calculate how much is coming here, and again x dot equal to 0. So x0 means once you are putting t equal to 0, so t equal to 0, that means this one will become, so at t equal to 0, once I am substituting, this will become 1. This one will become C1 into 1 plus C2 into 0. Yeah. So this is C1, and once we are doing that x0 dot, that will become your 0 into, no, 1 into, this is cos portion will be remained, so this will be C2 minus xi omega x0, another portion will be 0. Yeah. So now C2 will be x0 dot minus xi omega x0 divided by omega d. That will be your C2. So you can put it x equal to e to the power of minus xi omega t into C1. You can just put x0 cos omega dt plus x0 dot minus xi omega x0 divided by xi d into sin omega dt. Done. That way you can able to express the complete thing. So now let's see how these things should look like. So we have the MATLAB code. So here also you can see as like a last class. You can go to the editor, run. So it is first asking enter the value of the stiffness. So maybe I can just put it randomly, maybe 10. Then maybe I will put it 1 in kg. So enter the damping coefficient. So let's maybe first put it how much? Maybe 0.1. Then the initial displacement, how much? Maybe 0.2. And initial velocity maybe minus 0.1. Enter. So you see that damping ratio, critical damping ratio is so it is an underdamped system. So you see that how these things looks like. Let me just make it bigger. Yeah, so you are mostly familiar with the last time's one, that first one is the displacement versus time, then velocity versus time. Then this one what I was asking you in the last class, that if we try to look at from that side, how it should look like. So you now see that it's spiraling down. Okay, and if it is like a undamped, it will just keep revolving in that circle or ellipse, whatever, because the axes are changed, so it is actually ellipse. Okay. Yeah, so you can see that this type of graph you can see for the underdamped system. We can also quickly cross check how much is the coming the values. So damping ratio is this much. Yeah, so damping ratio was natural frequency is this much, damping ratio is this, critical damping ratio is 0.63, and we entered the damping 0.1. So 0.63, so 1.1 divided by 0.60, that is coming the damping ratio, that is the psi. Okay, so now, so we can see that already that damping ratio for this one, like once we put the K to 10 and M to 1, it coming 6.23. So now let's put something exactly 6.23. So now let's put that the damping ratio, first put 6.32. Something was there also, can't exactly recall. Okay, no issue, 6.32. And then initial displacement, so maybe now put it 1, and now we should not put negative, we can put it 0.2. Okay, perfect. So you see, very interesting. See the clear e to the power of minus psi omega t graph. It's just go and try to touch the zero. And also more interestingly, you can see how this graph is coming. So this starts from here actually. If you can see my cursor, it starts from here because we give the displacement 1 and velocity 0.2. So it starts from here, and then it actually coil down and come here. 0, 0. This also, it just go, come, and then become 0. So velocity has a reversal of sign here, but displacement does not. It's not crossed. It's just stay in the 0. So like this way we can get that. Okay. Although it was little bit underdamped, because if you see exactly the value was 6.234 something. You can quickly cross check. So I will just try to give little bit more value, 3234, and I give only 32. So 0.0046 is more. So you can see that damping ratio is still less than 1. It should be exactly equal to 1. Okay. So now let's do it exactly.
Sir, for exactly we have to put C critical matlab as it is.
I can put like square root of k by m.
That's also
That also, yeah. Yeah. So for this one, maybe I can just do it. So maybe 10, 1, and this one I am just using square root of
2 into
2 root MK.
2 into square.
SQRT. 2 root MK. Okay, so 2 into root MK. SQRT in by M into K, na? So
MK.
then 2 root MK. I think done.
Yes.
M into K. M is 1.
Yes.
Okay, done. So that's my damping. Now this is maybe putting 1. This is also putting 1. Now you see. Now this become exact critical damping. So you see, now it is not at all crossing anything or just come, and here it becomes 0. Okay. So we can go for a over damped. So once you're doing the over damped one, maybe I'm just running it. Maybe I can just put the same values. Damping, maybe I will just keep this time 10. Initial displacement maybe 1. So you can see it starts from 1 1, go, come, and then go like this. So this way these things happen. These are not giving that much of nice feeling because it's not oscillating at all. It's just gate and decay. But yeah, these are also the very important stuffs. So if we try to see that in what case, so what are the most predominant case we can encounter? That is the undamped system, definitely, because undamped systems are more predominantly present in the nature. If we see a regular oscillation or vibration, that is predominantly undamped vibration. So therefore we can see that vibration is means underdamped vibration, so that is like a oscillating and then slowly it comes into rest. But some of the critical applications, we try to design the structure for the critically damped. There is a very nice example of the door stopper that we try to design for the critically damped. We try that the door, once people are leave the door, it should go and stop. It should not just do oscillation, and it should not close before also. And it should not stop before, so that the door is not closed, so that the AC, air, and all those things will go out. So for the door stopper, people try to design it in the critically damped system. For some type of seismic design where the energy dissipation is very much required, we often try to go for the higher dissipation as well. Then the bike suspension and all those portions, we also try to go for the critically damped so that vibration can be very quickly absorbed. So based on the different applications, we try to do that. But suppose if you see a normal material and try to have the vibration control, that is generally underdamped most of the cases. So with this, we are concluding the today's class, and thank you all of you for attending the classes as well. Thank you.